Alright, welcome to the, I think, ninth video in this series, and we're going to actually go over the last derivative rule. After that, I'm not sure what we'll go into next. I'll have to think about it, but probably graphs, then theories, and then integrals. But let's get right into it. So our last derivative rule is if we want to take the derivative of a function that has some constant n to the x power. And notice that we're deriving with respect to x. So, like, if it was the other way, like the thing we're deriving to is in the base, then we know it's just the power rule. But this is a little different. We have we have the variable in the exponent. So this actually works out to just be itself times the natural log of that base. But let's prove it. I use prove lightly because this proof isn't as elegant as the others. Oh no, I'll point it out when we get there. So we have our fundamental derivative definition as delta x approaches 0, f of x plus delta x minus f of x all over delta x. And well, f of x is just n to the x, and we plug in x plus delta x into the function, so we get n x plus delta x minus n to the x all over delta x. And remember, we still have this limit, but I don't want to keep rewriting it over and over. But what I want to do now is make this a little more neat, and we can do this with some algebra. So this n to the x plus delta x can just be rewritten as n to the x times n to the delta x. And then we have the rest, n to the x over delta x. If you're a little confused by what I did here, it just comes from, like, if you have something like, if the bases are the same, then like n to the a times n to the b, it just equals n to the a plus b. Another way to put this, if we have like x squared times x cubed, it's just x to the 3 plus 2 equals x to the 5th, just that stuff. So let's back up and get right into this. Well, first, what I realize is we have those two things. So we can factor out the n to the x. And we get n to the delta x minus 1 over delta x, the whole thing over delta x. And remember, we still have this limit. We'll add it back right now. One thing I want to point out is this limit is with respect to delta x. We have delta x here, delta x there, but this is just regular x. So by the constant rule, like if you're deriving something that's not with respect to the variable you're deriving, you can just treat it as a constant and pull it out. And same thing with limits. Hopefully that makes sense, but because this is n to the x, not n to the delta x, we can just pull it out and say that n to the x times the limit as delta x approaches 0 of n to the delta x minus 1 all over delta x. So, I don't know, we kind of proved this part right here, n to the x. And then we still have this limit. And this is where I say, like, the proof gets a little ugly, because I actually don't know the rest of this proof. I don't know how to evaluate this limit very well. I do know that this right here simplifies to ln of that base n. but I don't know why. There's probably a video on it, maybe by Khan Academy, like, it's way better than me, like, why are you here? But, I don't know, gonna have to take my word for it, I guess. But, let's just move on. So, n to the x times ln to the n. And, that's our basic, like, definition of the exponent rule. So now let's go into some examples, and we have plenty of time left, so we can do a bunch of examples to make up for the lack of proof. So I'll just write the rule up top, just so you can keep it handy. And let's just go at some examples. So we'll start with 2 to the x. And, well, we know it's just f of x times ln of that base, you know? So we just get 2 to the x times ln of 2. And I believe ln of 2 is something like 0.69. It is some number, but it is just easier to write it as ln of 2. But what if we change the base? Because we're going to get something very special here. I should have said this at the beginning of the video. What if we have e to the x? Well, let's just try it out. So we got our function, n to the x stays the same, times ln of that base. Well, that base is e. And this right here, you might see where I'm going with this. Log base e to the e just cancels out and equals 1. You know, remember, ln is just log base e, the natural log. So if this just equals 1, then you're just left with e to the x. So the derivative of e to the x just equals e to the x. And that is something that's going to come really handy in the future for calculus. Let's move on. Let's say we have e to the 2x. So we have our function, and we take like the derivative of it, and well, it's just, let's say x equals 2x. This is a little confusing because, like, I don't know, x is like a general variable. You know, it can be anything, and in this case we're plugging in 2x. It'll make more sense when I go over u substitution. There's a lot of stuff I should have explained before this. Oh well. Yeah, so x equals 2x. So we just got our base, like n equals e, x equals 2x. So let's just plug stuff in. So e to the 2x times ln of e. But remember that when we're deriving with respect to x, this x right here, we also need to do a chain rule, because this isn't normal x up top. You also have this 2. So we need to multiply by the derivative of 2x, which was e to the 2x times ln of e times 2, which equals e to the 2x times 1 times 2, or just 2e to the 2x. And that is our answer. Hopefully I didn't lose you there. So let's continue. Let's do d dx of, I don't know, let's do some ugly numbers, like 43 to the 3x. So we have our basic rule here. N to the x equals n to the x times the natural log of n. So we got 43 to the 3x times, that's this part right here, times natural log of 43 times, remember, oh yeah, also, like, if it's e to the x, like, you can still do this chain rule thing, like, it would be e to the x times d dx of x, and this is just 1, so we don't really worry about that. But we don't have a regular x on top, we have 3x, so we multiply by the derivative. It's a little bit of chain rule right here, and you get 43 to the 3x times natural log of 3x times 3. That's pretty much it for like this concept. It's a good rule, but you won't use it that much. What you really need to remember is that the derivative of e to the x equals e to the x. And you just don't want to forget about your chain rule. Because, like, if you have something besides just x to itself in the top, like here, we'll do one more part. If we want to find the derivative of e to the x squared, then, well, we keep it as is. We have the natural log of the base, which just is 1. But then we also multiply, like the chain rule, the derivative of the top, which is x squared. So e to the x squared times 2x, and this is just 1. So you get 2x e to the x squared. And if we want to do it again, but with a different base, like, I don't know, 4x to the squared, then it is 4x squared times natural log of 4 times 2x, the derivative of the top. So I think that wraps up our lesson. I think it makes some sense at least. I'm sorry I don't know the full proof, but hopefully, like, the more examples made up for that. See you in the next video where we will probably talk about graphs.